Welcome from my side to the last day of the and the Mars day of the winter school. I will. Is it okay? Is it working?
Yeah, everything is okay.
Thank you, thank you. So I will just introduce Mars today, and I'm going to focus on sedimentary rocks and environments because you already saw most of the other geological processes in the other planetary body, and we thought that since sedimentary processes are very specific to Mars, it would be a good idea to focus on them here. So we will see how to map these deposits and why stratigraphy is so important. Very briefly, in this sort of family portrait, you know that Mars is relatively small. Its diameter is about as half as the one of the Earth. It's less dense, and as a result, its gravity is only about 1/3 of the one of the Earth. And we knew very little about its internal structure until the NASA InSight mission to Mars. Now we know that there is a crust which is from 20 to 37 kilometers thick. There is a mantle which is about 1,500 kilometers thick. And we know that there is a liquid core. What we do not know if there is also an inner solid core. We do not yet. Actually, in 2023, Samuel et al. Discovered that the lowermost part of the mantle consists of the molten silicate layer, and it is about few hundred meters thick. Mars has two moons, you all know, Phobos and Deimos. They are quite small. They have this weird, I would say, potato-like shape. And from the physiographic point of view, its most striking characteristics is this distinction between highlands and lowlands. I should add that this is a color-code topographic map with oranges and reds, which corresponds to higher elevations, and then down from yellow to green to blue to lower elevations. So the transition between the highland and the lowlands is generally sharp. In fact, it's referred as the global dichotomy, but in the area of Arabia Terra, only it's a gradual transition. Then we have this huge volcanic province of Tarsis, another big volcanic province of Elysium, some huge craters, Hellas, Isidis, and Argyre, and the famous fractured area of Valles Marineris. These are the most striking physiographic characters. Stratigraphically speaking, Mars has been divided in three periods: Noachian, Hesperian, and Amazonian. In Noachian rocks, or Noachian units better, are mostly constrained within the highlands. Then we have the Hesperian units in yellow. The Amazonian are mostly constrained in the lowlands and in Tarsis. Unlike Earth, Mars' geological surface is quite old, older than 2 gigayears, which means that geological activity on Mars is quite old as well. But Mars is not, geologically speaking, a dead planet, because there is still an active Mars. Even today, Aeolian dunes and megarypos are still active and forming and moving even today. Gravitative-driven processes are present, like landslides and gullies along the steep topographic surfaces. And polar layer deposits are forming, of course, in the poles with ice mixed with dust, water ice, I should add. Sedimentary rocks and processes are important on Mars because by understanding which processes shape them, in which depositional environments, we can sort of understand the climatic condition, and if we are lucky enough to observe a succession of these deposits, we can also observe an evolution through time of this environments, which in turn reflects how the global conditions changed through time. And this, since most of these, or many of these deposits are water related, has obvious implications in possible habitability conditions. The deposition environments, the sedimentary deposition environments which have been proposed on Mars are clastic sedimentary environments, such as in this case, where deposits sourced from a source area and through weathering and erosion processes are later transported by gravity, ice, wind, or water somewhere along this path, deposited, and then through the process of diagenesis will become sedimentary rocks. Since the source area is different from the depositional area, these are referred as allottonous deposits. Also, on Mars has been proposed the presence of chemical depositional environments, which are instead autochthonous deposits because they form in the very same basin in which they were sourced. For example, like evaporitic rocks. Impossible relations with clastic deposition environment, which can be, for example, fluvial, like in this case, but also aeolian, which is a very, very consistent case on Mars. Sedimentary deposits are widespread all over the planet. In this map, which is not very new, but it's anyway still correct, they are indicated by means of when they were found on high resolution data sets, high-rise and narrow angle. You see they are widespread all over the planet, but mostly in the highlands. And if we can put together the geomorphological characteristics of these deposits together with the mineralogical hints that we can derive from spectral data together with the stratigraphy, we can derive this kind of sedimentary mineralogical evolution. So we can see that until the mid-Noachian, clay-bearing deposits were dominating. These clay-bearing deposits are not always, but or very often associated with water-related, mostly fluvial depositional environments. And from late Noachian to all of the Experian, these deposits start to be interbedded with sulfate-bearing deposits. This evolution suggests a transition from water-rich conditions until the mid-Noachian to increasingly water-limited conditions up to the end of the Experian. Then, in the Amazonian, ferric iron oxides dominates, suggesting the transition to the extreme hyperarid condition that we know today. Now, if we want to map these deposits, we need to face basically the same problem of all remote sensing method, but I would say even more than in the other cases. Why? Because sedimentary deposits tend to be small deposits in volume and scale. So in a remote sensing method, scales are instrument dependent. So even in interested geological maps, we have geological maps at all scales, but on Earth, this is our choice. If I am mapping, I'm in front of my outcrop, and accordingly to what I want to convey in my map, the science I want to do, or the technique I want to do, I will decide the scale of my map. On Mars, on the planets, in remote sensing method in general, we cannot do that. Our work depends on the instruments, on the scale of the image that we have. Plus, on the planet, we have a remote sensing with no or very limited ground truth. We have very few rovers on the ground on Mars. And we have limited information on rock composition. I just told you that we have some mineralogical hints, so we know something about mineralogy, but we don't know the actual rocks that corresponds to the units we are looking at. On the other hand, we have relatively limited weather, which implies a very good preservation of morphology. This is the reason why traditionally in planetary mapping, not only in the sedimentary system, the cartography has always been mostly chronostratigraphic or morphological rather than the geological map we are used to on Earth. And this is also the reason why we have problems of scale and equifinality we have to deal with. I already mentioned the problem of scale as instrument dependent. Here we have the same area covered here by HRSC with a resolution of 25 meters per pixel, and we can distinguish morphologies. If we switch to CTX images with a resolution of 6 meters per pixel, we can better discriminate this morphology. We can actually see that the fan shape deposits actually correspond to more fan-shaped deposits, that there are channels on top of it. But we can also see two geological units, a light tone one and a darker tone one. If we switch here to high-rise resolution with 30 centimeters per pixel, we can observe actually the internal geometry, the layering here of the two units, and we can characterize the stratigraphic transition between the two units. Now we have to remember that we need all of these data sets to understand the units and to constrain the boundaries between the units, and of course for the following scientific interpretation. But at the same time, we have to remember that in our map, we really need to be consistent throughout all of its extension. So when we select the scale of work that we need for what we need to convey for our science goal, we need to keep this scale consistency. To be more clear, we cannot map at high-rise scale if high-rise do not cover all of our study area, which is normally the case. But of course, we need to use high-rise images to better understand and describe the units. Other problem of scale, it's the obvious problem of that we cannot observe, touch the rock in the outcrops. If we are skipped to the scale of the geological context, let's say from the test to 100 kilometers of scale, there is no big difference between the kind of geological reconstruction we can do and represent on Earth and on Mars, for example. But if we switch to the geological, I would say to the outcrop scale, so observation, measurement, facies definition, we have here on Earth and on Mars similar landforms. We have similar polygonal pattern, even with similar scale, but on Mars we are stuck here. While on Earth, we can, even without taking the samples to the lab, we can clearly see that our unit consists of precipitated crystals, so it's an evaporitic rock. Moreover, we have the problem of equifinality, which means that similar effects may be generated by different combinations of causative processes. Same mounts, they might be formed as erosional remnants, so they might even not be depositional features. They might be pingos, so formed in glacial settings, or volcanoes, or spring mounts. And I'm not even mentioning all the volcanic or volcano-sedimentary processes that might originate similar landforms, which means that and also this is not an academic exercise, because all of these interpretations have been proposed in different parts of Mars with based on solid observation. So this is a problem. And in order to cope with this problem, we have our only instrument is to integrate all of the data and define a geological context. context. This means that we have to switch from the interpretation of the single landform, for example, the mound I was showing you before, to the interpretation of associated landforms, so which basically means to reconstruct a landscape. In order to do this, we need to reconstruct the lateral and vertical distribution of the different units, so to not to interpret together units or morphologies which were formed in different stages of the history of this basin. In order to do this, we need to realize the geological map, and in doing the geological map, to understand the stratigraphic relations between the units. Then we will be able to interpret genetically our units, our geological units, using the classical multiple working hypothesis approach and always analog studies. We will formulate the genetic hypothesis, following the consequences of these different hypotheses, and test this hypothesis with the classic hermeneutic cycle. Stratigraphy, so it's the base to start a work, and as a base is still based on the principle of stratigraphy by Steno, 1669, which allow us to reconstruct the relative dating of the geological units. We can reconstruct this relative dating and show it in a space-space or and it's better to do both of them, space-time diagram. Space-space diagrams are aimed at reconstructing the geometry of the units and the geometry between the different units. So, for example, here we have a crater margin. At the base of the crater, the impact breccia, then some evaporites were deposited and then slumped. Here, these units are cut by a following channel, fluvial channel, which deposits some fluvial deposits here. Then, at the end, overall succession is covered by this recent dust. This reconstruction is very effective to show the geometric relations between the units, but lose one thing, the meaning of time, and especially of the missing time, because we have some time which is not represented, for example, between the deposition of the volcanic rocks which were cratered and the input breccia, for example. In order to do this, we use the space-time diagram. In this case, we lose the meaning, the geometric meaning of the different units, but we gain the one of the missing time. For example, we know that the crater margin, the volcanic rocks in the crater margin were the first to be deposited. Then sometimes an erosion passed before the cratering event occurred. Then after the cratering event, some other time occurred before the evaporitic rocks were deposited and then slumped. Then other time before this channel incision in this part of the basin, then this channel stopped to erode and started to deposit, so sometime even here, and at the end, the recent dust. Of course, we have no clue about the length, the precise length and precise dating of these ages and of the time which is not represented. We need crater counting in order to better define this map. But we know for sure, for example, this time is longer than this time, but still we know that there is a discontinuity between this part of the succession, which means there is an unconformity. And this is an example of an unconformity on Mars. We have this picture is taken by Curiosity rover in Gale crater. We see this layered deposits here with this bed attitude, and this we see that these beds are cut here, though there is erosion. This is an unconformity, and on top of this we have this layered units with another layer attitude. So some time here is not represented and it is missing. to try to explain why it is important to define unconformity and which are the consequences of this on science, I take an example from the Eberswalde delta-like feature. This is a very famous place on Mars because it is considered to be the smoking gun to prove the presence of persistent water flow on Mars. When at the time of when it was discovered in 2003, there was a big discussion whether water was only catastrophic, consisted only of catastrophic flow on Mars, or even if persistent flows were possible. And this looked like to prove without any doubt these persistent water flows. But then olivine was detected in this crater in correspondence of this delta, and this is not actually very consistent with fluvial activity. But if we go closer in this deltaic lobe and even closer here, we see that this delta corresponds actually of two geological units, this layered light deposits and these darker tone deposits. And if we see the boundary between these two units, we see that actually these dark tone deposits cut the light tone deposit. This means that there is an unconformity with between these two units, which means that they belong to two different stages of the geological units in this part of the basin. And actually, the A2 abundance show that the water bearing minerals are confined within the light tone units and not in the dark tone unit, which is the one with the olivine distribution. So the olivine rich deposits lie above the unconformity, and they correspond to another part of the history of the of this morphology and of this basin. In order to try to reconstruct correctly the stratigraphy, we need to pay attention to some layer terminations and geometry. Now I will focus on the erosional truncation that we just saw, to the on-lap geometry, which is this one, and to the off-lap geometry with the down-lap termination. The erosional truncation here is probably better, more clear than the one I showed you earlier. You see these light tone deposits, which are cut here and then covered by this unit, this dark tone unit, which is not conformable and was deposited after the erosion of these light tone deposits and after some time that occurred. And so basically we have an interaction of the deposition here and then another phase in the history of the basin. On lap, we have this horizontal strata which terminates against an inclined surface. You see here this unit embays this other unit with this fashion. It means that I am infilling the basin. Maybe this is more clear in this other example. We have a crater margin here and these layers which overlap against the crater margin with this fashion here. It means they are infilling the basin. Then off-lap, down-lap. Off-lap, we have strata which are prograding into deep water and terminating in this deeper basin. Down-lap is a relation in which, initially inclined strata terminate against an initially inclined, an initially horizontal surface. For example, this is an example of down-lap taken on Mars by, again, the Curiosity rover. You see this inclined strata which are prograding and the basal termination is a down-lap. It means I'm moving my sediments in this direction. Then we have lateral transition. Lateral transition if we have lateral continuity, it means that deposits are coeval, are conform to water law. It means we are speaking, we are defining two contemporaneous environments in my basin. For example, here we have layers and mounds, and if we go closer in 3D, we see that layers continue inside the mounds. It means that these two units were formed at the same moment during the same stage of formation of the basin. So moving towards mapping, we have processes. Sediments are moved. In this case, this is an example of an eolian depositional process. So we have some clasts which are moved. And with time, we can see these processes only if we are there when this happens. But with time, these processes will form landforms, such as, for example, this dune. Interestingly, landforms are short-term features on Earth, so basically only quaternary features, but on Mars, they are long-term features. So they go deep into the geological record, in the deep time. With time, superposed landforms form deposits, which are long-term features on Earth and on Mars. But in order to see them, sorry again, this is controlling me and not vice versa, they need erosion and exhumation in order to be seen. In principle, when we map landforms, we realize a geomorphological map, and when we map deposits, we realize a geological map. This happens on Earth. But on Mars, speaking of geological maps is not trivial, because actually we have no lithological information. We discussed about that before. And geological maps on Earth are based on lithological information. So somebody actually argued that we cannot even speak of geological maps on the planet. But still, the goal of geological maps is to perform the most objective as possible representation of my area. So we can use what is our most objective means and distinguish the basis, the units on the basis of this objective means. So the characteristics of the deposit, their color, texture, that they are layered or layered, if they have sedimentary structures. Then we can look at the morphologies, not as genetic interpretation morphology, but simply as description, for example, the mounds we saw earlier, and of course, stratigraphic position within the succession. This is an example. Again, the Eberswalde delta-like feature, we have a substratum, which is this one, which is massive to brecciated. Then we have the light tone materials, which can be layered and non-layered. We have the dark tone material we saw earlier, and we have unconformities between the substratum and the light tone deposit, and this is the unconformity we saw before between the light tone deposits and the dark tone deposits. But if we want to focus on the genetic origin of this feature, we want to focus on the delta evolution of this area. What we need to do is like to imagine, to strip away the dark tone deposits which are on the top of our light tone deposits, which are the object of what we want to focus on our science point of view. And so we will interpret only the light tone deposits. Imagine that the dark tone deposits do not exist here. So channels, for example, rectilinear channel, meandering channel, interdistributary areas. This is the delta plane. We have the delta front here and the prodelta. This is a totally interpretative method, genetic interpretation between units which were deposited at the same time. I think I am a bit long, but I would like just to conclude with very quick few seconds of remark. I told already 10,000 times that it's important to switch from the interpretation of landform to the landscape, but I'm telling you this once more, because a fluvial channel, for example, is part of a system. It will never be alone. For example, it could be associated with alluvial fans, floodplains, or whatever. Then try to include your system in a geological context. So try to understand the geological context of your basin, the stratigraphy of your units, even outside of your basin, and try to understand the context in this, meaning where do the sediment come from? Source area should be somewhere, and try to interpret all of your evidence at all scale.